So there are different types of voltage converters. There's, depending on the input and output. So the input could be AC or it could be DC, which stands for alternating current and direct current. So the four combinations of those are AC to AC power converters, AC to DC, DC to AC, and DC to DC power converters. The most straightforward and simple power converters are the DC to DC power converters, which basically they take a constant, steady, direct voltage, say like 12 volts, and they convert it into another voltage, say like 5 volts. That would be a step-down converter. So from that, we can tell that there are several different types of DC to DC converters. It could be a DC to DC step-down converter or a DC to DC step-up converter. Even within the category of DC to DC converters, there's different types of converters, and different types of converters have different levels of complexity. Some converters have 2 capacitors and 2 inductors. Some of them have several transistors and diodes. At the fundamental level, the way a converter works is that it uses switching components such as transistors and diodes to sort of facilitate or regulate the energy being stored and taken out of energy storage components such as inductors and capacitors. And in electrical circuits, inductors and capacitors can be used either as filtering components or as energy storage devices. And in this case, they're used as energy storage devices. So an inductor can store energy in you can visualize it as being kinetic energy being stored. And capacitor stores potential energy, the potential to generate a voltage. And the inductor sort of stores the capacity to generate a current. Personally, I believe that power converters are one of the most important technological developments of our time. We see with almost all the electrical devices that we use today, there's an associated power converter. So our laptop chargers, our mobile chargers, all the appliances that we use at home, all of these have a power converter that takes energy from the grid and converts it to a voltage that the device can use. Even within our phones, there's several different power converters. Just because there's several different devices in our phones that use different voltages. Our LED light that flashes our cameras, for example, the camera itself, the screen, and all these different components need different voltages to operate properly. So even within our phones, there's several different voltage converters. I'd say the most fundamental and straightforward type of converter would be the buck converter, since it only uses one inductor, one capacitor, and one pair of switching components, which would be one transistor and one diode. The idea of a buck converter is to take in a constant voltage and step it down to a lower voltage, depending on the switching frequency of the transistor and depending on the duty ratio of the transistor, which is how long the transistor is kept on. So there's no one converter that is ideal or optimum for all applications. It always depends on the application. So a buck converter could be the ideal application, the ideal converter for applications inside a phone. And a flyback converter, for example, which is a converter that uses a transformer for isolation, could be ideal for high voltage applications to isolate between the consumption part of the converter and the input part of the converter. If we look at the buck converter, we know that there's 2 different modes of operation, and that applies for all converters, but we're just using a buck converter as an example. There's discontinuous conduction mode and there's continuous conduction mode. Discontinuous conduction mode means that the inductor current, or the energy stored inside an inductor, goes to 0 at least once per cycle. While in continuous conduction mode, the inductor current never goes to 0 throughout the entire operation of the converter. Alright, so this is what a typical buck converter looks like. It includes a transistor, a diode, an inductor, a capacitor, and a resistor. And the state of the converter changes depending on the switching of the transistor and the diode. The first state is when the transistor is conducting. The second state is when the diode is conducting. Now, since we can't analyze both states simultaneously, what we do is that we take the average between the 2 states. So first we look at the inductor voltage, the voltage across the inductor, and then the current going through the capacitor. We know that the average inductor voltage needs to be 0 due to the properties of an inductor. And similarly, the current going through a capacitor averages to 0 across one switching period. The first state is when the time is between 0 and dTs, where d is the duty ratio and Ts is the switching period. The inverse of Ts would be the switching frequency. Now if we take the average of the inductor voltage, that gives us the relationship between the input and output voltages. So the output voltage is equal to d, the duty ratio, times Vg. Similarly, we can find the average inductor current by looking at the capacitor current. That gives us that IL is equal to V out over R, or dVg over R. And the next step would be to look at the waveforms of the current going through the inductor, capacitor, and the voltage across the inductor. That gives us the ripples that we need to analyze the circuit. Based on the fundamental equation of an inductor, we can find the current ripple, the inductor current ripple, based on the voltage levels of the different states of the converter that we analyzed before. This gives us the following inductor current ripple. The inductor current ripple tells us whether the converter operates in DCM or in CCM, which we'll see in a bit. If we do the same thing for the capacitor, we can find the capacitor voltage ripple, as shown here. In terms of mathematical equations, that gives us that the inductor current ripple is proportional to Ts, which is the switching period, which means that it's inversely proportional to the switching frequency, and it's also inversely proportional to the inductance of the inductor. In terms of the capacitor voltage ripple, it's also proportional to Ts and inversely proportional to both CL and L, C and L. For DCM, the average inductor current is less than the current ripple of the inductor. For CCM, it's the opposite. The average inductor current is greater than the inductor current ripple. So for a given delta Vc, which is the capacitor voltage ripple, L is actually inversely proportional to C, which means that if we have a big enough capacitor, then we can actually reduce the size of the inductor that we need. Now let's look at the water analogy that we use for this project. First, we look at the capacitor. For an electrical capacitor, the energy stored inside the capacitor is equal to half C capacitance times V squared. The other equation is the fundamental equation of the capacitor. The analogy is drawn is that the pressure is analogous to voltage and the flow rate is analogous to current. For a water column capacitor, which is what we're using here, the flow rate going inside into the capacitor is equal to Q. If we do a mass balance on the mass going inside the capacitor, the water column, and the mass going out of the control volume shaded in red, we get that rho Q is equal to dH by dt A times rho. Substituting the pressure equation, that P is equal to rho GH, or H is equal to P over rho G, we find that Q is equal to A over rho G dP by dt. This is the same as the equation that we have for an electrical capacitor, where the water capacitor is equal to A over rho G. Now if we analyze the energy stored in the water column, we find that a differential energy element is equal to Hg times the differential mass element. The differential mass element can be written in terms of the density times the volume. This gives us that the total energy stored inside the capacitor, the water column capacitor, is equal to A over rho G P squared over 2. Notice that we get the same term for the water capacitance. Also, if we compare this to the original equation for the energy stored inside an electrical capacitor, we find that it has the same form, half CV squared. Now we move on to look at the inductor. For an electrical inductor, the energy stored inside the inductor is equal to half L the inductance times I squared. The other equation that's important to us is the fundamental equation of an inductor. For this project, we're using a simple water tube as an inductor. The pressure difference across the terminals of the water tube is P. The length of the tube is L. Doing a simple momentum balance, we know that M dV by dt is equal to the force. Placing M with the density times the volume and V with Q over A gives us the following equation. Placing force with P times A gives us PA is equal to rho L dQ by dt. Comparing this with the fundamental equation of the inductor, we find that rho L over A is our equivalent water inductance. Next, we look at the kinetic energy of the water moving inside of the tube. Representing the kinetic energy equation, half mv squared in terms of density and flow gives us the following equation. Mass can be represented in terms of density times volume and velocity in terms of flow divided by area. Simplifying this gives us half rho L over A times Q squared. If we compare this to the energy stored inside of an electrical inductor, we find that it has the same form, and we get the same term for the water inductance. Alright, so here's a full picture of the actual working model. So all the components are labeled, and at the bottom here we have the ground, which is open to air, giving it the atmospheric pressure. Then we have the pump, which acts as our voltage source. Then connected to the pump is our voltmeter, or pressure gauge, which shows us the pressure of the pump. Connected across from that is the transistor, or the solenoid valve. The solenoid valve is controlled by an Arduino and a circuit and transistor circuit, which is connected to a power supply. This controls the duty ratio of the solenoid valve and the switching frequency. Next, we have our diode, where we use a check valve. This is connected in parallel across the transistor and the ground node to allow current to flow even when the transistor is not conducting. Next is the ammeter, or the flow meter, which shows the flow of water through the inductor. On the bottom we have our output voltmeter, which shows us the pressure across the capacitor and the resistor. Here's the capacitor that stores energy in terms of height, the resistor where a hose clamp is used, and finally that's connected back to ground. From left to right, the measurements shown here show the input pressure, the flow through the inductor, the capacitor water height level, and the output pressure. This is the case for when the duty ratio is set to 0.5 and the frequency is set to 4 Hz by the Arduino. Notice that the output pressure is approximately half of the input pressure, which is 2.5 psi, which is what we expect from our equations. Setting the switching frequency of the solenoid valve to 4 Hz gives us a very small inductor current ripple. This forces the converter to operate in CCM. It also means that the output pressure ripple is very small, as we can see. The next case to look at is for a duty ratio of 0.6 and a solenoid valve switching frequency of 0.5 Hz set by the Arduino board. This means that the solenoid valve switches with a period of 2 seconds. This increases the inductor current ripple and forces the converter to operate in discontinuous conduction mode. If we look at the inductor current, the flow through the inductor, we can see that it goes to 0 at least once per cycle. We can also see that the output pressure ripple has increased drastically compared to the continuous conduction mode case. Also, if we look at the water level of the column capacitor, variations have also increased, as we expect. For the next case, we keep the switching frequency constant at 0.5 Hz, but then decrease the duty ratio from 0.6 to 0.3. What we see is that the water level in the capacitor decreases to almost half its original value. Since the switching frequency is still at 0.5 Hz, the converter is still operating in discontinuous conduction mode, and the inductor current ripple is very large to the extent that the inductor current goes to 0 at least once per cycle.